back to the University of Kansas Physics and Astronomy Colloquium. Today we have Richard Woodard of the University of Florida. Professor Woodard did his PhD at Harvard in 1983. He was a postdoc at Santa Barbara, Brown, and Austin. He's been at Florida since 1989. He's extremely distinguished, a world expert on gravity and quantum gravity, and we're very proud to have him here. And the topic will be quantum gravity comes of age.
Okay, thanks very much. It's a great pleasure to be here. I was born and raised in Kansas, and I've spoken, I think, on every continent except Antarctica, but this is the first time I've been to the University of Kansas, so it's a great pleasure to be here. Let me just see if I can...
The button doesn't work.
Buttons don't work, so I'll do it manually here. So I promised when I agreed to do this to not go beyond what a first-year graduate student should know. Of course, I'm a particle theorist, so you must be used to the idea that we lie a lot. But in this particular instance, I'm going to try very, if you promise not to tell my colleagues, I will try very, very hard to adhere to that. I need to tell you first a little bit about what quantum gravity is. I'm not going to give you Einstein equations or quantum gravitational loop expansions or anything like that, just in the rough basics of it. So quantum gravity is the combination of three things: gravity, relativity, and quantum mechanics. They each have their own coupling constants, g, Newton's constant, c, the speed of light, and h bar, the quantum mechanical, the reduced Planck's constant. General relativity is the combination of the first two. It's what happens if you take gravity and make it relativistic. It works great. You've probably all heard that it gives a perfect, as far as we can tell, a perfect theory of gravitation with all the tests that we can do, which are now getting to be quite precise inside the solar system. And we're all hoping very much that when the LIGO people turn on and have the new enhanced LIGO sensitivity, that they will actually detect gravitational radiation, too, another key prediction of it. And so you might at this stage say, ha, Professor Woodard, what are you telling us that this theory is so great if you're telling us that it's just the combination of that theory with quantum mechanics that makes it so bad? That is, how can it be that this theory is so good if you just add h bar and make it non-zero, it turns out to be so bad? And I recall being very confused about that when I started out studying this theory way back in graduate school. I imagined some wrong things. Perhaps you all imagine them too. Let me just debunk them. It is not that there are some different equations of quantum gravity than there are of classical gravity. In fact, in the Heisenberg picture, the field equations are exactly the same as general relativity, not a bit different. And it means exactly the same thing to solve them. It means to express them as functions of time and the allowed initial value data. The one only different thing is what those initial value data are. And that's a complicated word, just saying the initial positions and initial velocities, initial time derivatives of the dynamical variable. The only thing that's different about quantum mechanics is that quantum mechanics has this key principle called the uncertainty principle, which says that each of the degrees of freedom, you cannot set each element of a conjugate pair, the initial position, the initial velocity, you cannot set each of those equal to zero. You have to have a little bit of motion in each of them called zero-point motion. No problem for atoms, and in fact it's what keeps atoms stable. But it's the origin ultimately of the divergences that occur in quantum theory, and it's the reason why this perfect theory of classical physics gets so completely screwed up when you turn on quantum mechanics, because when we say that it gives a perfect theory of classical physics, what we mean is if we take the classical field equations and compare them with data, there are solutions to the classical field equations which agree perfectly with what we see. But doing that means that we have turned off almost all the degrees of freedom. You can do that in classical physics, no problem at all. You can set both p and x equal to 0 in classical physics, no problem at all. And that's what you have to do to get this perfect agreement. When you turn on quantum mechanics and turn on quantum gravity, you cannot do that anymore. They have to each have a little bit of motion in it. You might think, well, that's just a little bit, so it's no big deal. But each position, it's a field theory, so each position, actually, morally speaking, has 2 degrees of freedom, and there are a lot of points, unless they've changed something about the universe since the last time I checked, there are a lot of points. And that means that, that you've got an infinite number of these things, or at least a very, very large number of them, and they each have to have a little bit of motion in them, and it's that thing which is screwing up gravity, screwing up quantum gravity, which is making this perfect classical theory be such a downer for all of us who like to do quantum physics. So let me be a little bit quantitative about that. I wish to God that we could do exact calculations in quantum gravity, but that would be asking more than we can do in any other interacting quantum field theory in 3+1 dimensions. We can't. All we can do is something called perturbation theory, where we just expand it in a power series. And it may well be that the act of doing that is what's giving us the crazy results. In any case, if you do that, what the theory churns out is an answer like this. So no matter what kind of a question you ask, you get an answer that looks like this. So it's got an h bar and a g in it. That's the hallmark of quantum gravity. And for dimensional reasons, it's got a 1/c⁵, and then it's got some characteristic frequency. Those things are in any kind of a prediction, and then it's got a characteristic frequency of whatever thing you're measuring. So for example, if we were looking at quantum gravitational effects with FM radio, it would be that frequency. Okay, and then the so-called tree order prediction is this, and then the theory predicts a series of corrections that look like that. And the theory, the problem of quantum gravity is really twofold. First, for any omega that we can reach in any measurement that we can do down here on Earth, the frequency is hopelessly too small for this number to be a measurable number, for this kind of result to be a measurable number. For example, for FM radio, this number would be 10⁻71. You might think we could do better at the LHC, and in fact we can, but it would still be 10⁻31 or 32. Hopelessly too small to see. We can measure maybe 16 decimal places, we cannot measure 32. Just hopelessly too small to see. And that, by the way, means something. I'll tell you what that means in a minute. Second problem is that these numbers, alpha1 and alpha2, wind up being infinite. So there's sort of two problems. We're stuck between measurable 0 and infinity. So for example, one prediction of the theory is that when I shake my hands like this, I'll produce gravitational radiation, and the theory predicts that I produce so much gravitational radiation that you were all fried to crisps of bacon. Well, I'm not very good in physics lab. I'm the first to admit that, and my lab instructors would back that up to any degree that you request certification of that, but I think I just did that experiment, and the theory's a little bit off as far as that one goes. But assuming that we were able to solve that little problem, or to say it in a more graphic way, what is it, 15% of the American public believes that they've been visited by aliens, that not only do aliens come down to Earth, but that aliens have actually personally abducted them and performed bizarre sex experiments on them. Okay, so suppose the aliens landed here, and they walked out and they said, Richard, look, we have had civilization for 1 billion years, and we actually are able to build accelerators big enough so that that number is of order 1, and we've tested it, and the result is n=8 supergravity. And then another alien came down, suppose the Greys tell us that, and the beta reticulans come down and they say, no, don't listen to the Greys, they do all these awful experiments on us, listen to us. We've done experiments on that, and we tell you that it's type 2b superstring, or superstring theory. Who are we going to believe, and why? We can't actually ourselves test this thing. So even if we could solve this problem of coming up with a theory which was predicting something less than divergence, craziness for the problem, we wouldn't be able to subject it to meaningful experimental scrutiny to figure out what's going on. Well, I've sort of skipped a step there because there actually is an answer to that put forward by my string theory colleagues, and that is that mathematical consistency is going to be so powerful and so restrictive that we won't have to, that there'll only be one way to do it. That problem of trying to do a measurement, the old-fashioned way of building physics up from observation and experiment, is just passé, and that just using mathematical consistency will be so great that, that they'll be able to just completely fix the theory. Well, that was before the acceleration measurements about the universe accelerating. They've now changed the theory so that there's something like 10⁵ different versions of the theory. and you can get basically any answer you want out of it. But at sort of an intermediate level, they were claiming, and this, let me not criticize them. This is their own words. This is string theorists' words. Big question in M theory put up by a string theorist. So the big questions are fundamental principles. What are the fundamental degrees of M theory? That was what they were calling string theory then. So they don't know what the dynamical variable is, number one. Or does this question even apply? Is it time to abandon the reductionist paradigm? For those of you who were educated in American high schools, that means, does it mean that we have to give up physics as we've understood it since the days of Newton? Go back to magic. Number two, what are the dynamical laws governing them? So number one, we don't know what the dynamical variable is. Number two, we don't know what equations it obeys. And number three, we don't know what observables they are. But other than that, there has been enormous progress in the last 30 years, and we're right on the verge of being able to pin things down to within 10 to the 500 different predictions about what things might be. Well, I don't know about you, but this reminds me of a comment that Gertrude Stein, the famous commentator of the Lost Generation of Americans, said about her hometown in Oakland. She said, the trouble with Oakland is that when you get there, there isn't any there. Or to make another quote, you know, again, I'm just quoting their own words. This is a famous string theorist being told about the initial data, which later on in 2011 was given the Nobel Prize, that the universe is accelerating. He said, I'm sure the data is wrong. He didn't know how to form the plural in Latin. I'm sure the data is wrong because string theory predicts a negative cosmological constant, and indeed it did used to predict that. And if it's right, I'll quit doing physics. Well, opinion differs about whether he quit doing physics. He's still doing string theory. So the long shot, the upshot of all that is that I think, with all due respect to my colleagues in string theory, who are brilliant men, I'm making fun of them, of course, but they are brilliant men, and they're doing the best they can, but I just don't think that mathematical consistency is going to be enough to answer those questions. We really need data. And the burden of what I want to tell you about today is that we're getting it, a lot of it, with a lot more on the way, and that it is actually, I think, going to slowly, painfully, the old-fashioned way, draw us forward into an understanding of quantum gravity. It's already changing the way it is that we're thinking about quantum gravity, and it's bound to do more in the future. That's the burden of my talk today. Okay, that's coming to us from cosmology. And again, I promised I wasn't going to go beyond what a first-year graduate student would know, but every first-year graduate student, I think, if they have had Jackson E&M, does know that if you wanted to, suppose you were out on a hot date, and your girlfriend or boyfriend asked you, you know, could you just in one line tell me all this nonsense about special relativity? That's the line I would write here. That encapsulates all of special relativity right there. The invariant element is that. And it says basically that the parameter t is measuring time, and that the parameter x is measuring physical distance, and that in different frames they combine together in such a way that that thing's a constant. Okay, that's all of special relativity, aka flat space. If you go to the next most complicated geometry in general relativity, and I won't tell you how we're doing it or anything, but if you go to the next most complicated one, the only thing that changes is you put in a factor over here called the scale factor. And the reason for its name is that it's telling you that unlike here, x is no longer giving you physical distance. To get physical distance, you need to take a coordinate separation x and multiply it by the scale factor, a of t. Hence the name scale factor. You have to rescale what the coordinates are. And when a general relativity geek tells you that the universe is expanding, what he means is that a of t is increasing as a function of time. Let me just jump to here. There are two time derivatives of a that are relevant. One of them is called the Hubble parameter, h of t, and it is a dot over a. And the other is called the first slow roll parameter. It's symbolized by epsilon of t, and it is minus h dot over h squared. This is dimensionless. This has the dimensions of 1 over a time. Okay? The way it is that general relativity tells you how to figure out what a of t is by using the Einstein equations. And for this special, very simple, this is the simplest geometry you can be dealing with that's not flat. For that simple geometry, the two non-trivial Einstein equations take this form. 3c squared h squared is equal to 8 pi g times rho, the energy density, the energy per unit volume, and minus 3 plus 2 epsilon times c squared h squared is equal to 8 pi g times p. And then the way it is that you work is you have to have a model for how it is that rho and p depend upon a, on the scale factor, and once you have that, you plug it in and then solve the equation. For example, suppose you believe that the universe consists of just non-relativistic matter. Well, then the energy density is just the rest mass energy, and if you increase the volume of it, you decrease the density just by 1 over a to the third, so it should go like some constant over a raised to the third power. The pressure should just be 0, because you remember we're measuring it with respect to the rest mass energy, so the pressure is effectively 0 compared with that huge energy. And that would give you some equations that you could then just solve for A, and you would get that A grows like t to the 2/3. Same thing if you said that it was consisting of just radiation, of ultra-relativistic radiation, then P would be 1/3 times rho, which many of you know from your study of condensed matter physics, or statistical mechanics, and the energy density would fall off like 1 over a to the 4th. You could plug that in, and that would tell you that A would grow like t to the 1/2. Okay? So that's basically how you do it, and I'm not going to tell you any more details, and you don't have to know any more details. Okay, these guys have been measured. So a lot of you know these beautiful pictures that have been produced by the Hubble Space Telescope, right? And you might have thought that physicists and astronomers paid the $1 billion that we American taxpayers paid to put up the Hubble Space Telescope to produce those pretty pictures. But of course, if you think about it a little bit, you know that that's not right? I mean, we're evil. We're the guys who made nuclear weapons, and frankly, the reason there's anything left on this planet alive is not due to us. The military and political leadership just wouldn't go along with what we prepared for them. And so we didn't do that to produce the pretty pictures. We did it for another reason. The reason the Hubble Space Telescope was put up was to measure the Hubble parameter to within 10%. That was the so-called Hubble Key project. Actually, we can do quite a bit better now with the cosmic ray microwave background data, and I think that's the latest result for it. It's quoted in this funny set of units of kilometers per second per megaparsec. A megaparsec is a distance of length that astronomers use. So here you have a length and a length. You can see that they must cancel out. You could convert it to a pure frequency. It would be about 2 times 10 to the minus 18 hertz. Okay, so the universe is expanding right now, but very slowly. And this first slow roll parameter, the measured value of it, and it blows my mind that they have this to two significant figures, is 0.47 plus or minus 0.03. Amazing. Okay, well, I need to give you a cautionary tale about all of this stuff, and the cautionary tale has to do with this problem about the sign choice that Benjamin Franklin made. You recall that there were 2 ways of producing electrical charge, rubbing glass with silk and rubbing amber with fur, and Franklin had the brilliant, they first thought that there was 2 kinds of electricity. Franklin had the brilliant insight that what one of them was just the dearth of the other one, and he made an arbitrary choice about what to him seemed like an arbitrary choice about what the sign was. Unfortunately for us, he chose the signs in such a way that the electron, which is the basis of our electrical power generation industry, has negative charge. So now generations of electrical engineers and physicists have to remember that if you have a positive current going that way, what's really happening in the wire is that electrons are moving that way. I don't know about you, but I hate that. Almost everybody who has taken electrodynamics, especially people who've talked about the Hall effect, they just all hate that. It's so confusing, so awful. Physicists like parameters, arbitrary parameters, to be positive. If we can possibly arrange that, that's what we would do, so that we can just look at the equations and we don't have to remember, oh, no, that parameter is negative. And we can just read off the signs of the way things go. And that's so frustrating that one of my one of my engineering students, showed me this cartoon that was posted on the internet about an electrical engineer who was sent back to stop a robot apocalypse in a time machine, but in fact the thing that he thought was most important to stop was Franklin's sign choice. Okay, so we physicists, we clever cosmologists, we clever theorists, were just so sure that before 1989 that the universe had to be slowing down. We were so sure of that for the same reason as you tell the P1 students. When you throw something up, you may throw it so fast that it escapes, but it slows down a little bit, right? The gravity causes it to slow down. We were just sure that that had to be happening in cosmology. And we were therefore certain that the second derivative of the scale factor absolutely had to be negative, and we didn't want generations of future physicists to be stuck with the same awful kind of sign choice. So when we defined the parameter that was going to measure acceleration, instead of making it an acceleration parameter, we made it a deceleration parameter. We put that minus sign in it. We made it a double dot over a dot squared. Okay? However, sometimes you win, sometimes you lose. When the measurement was actually done in 1998, the measured value came out to be negative. The universe is accelerating right now. The sign is positive of a double dot rather than negative. And the moral of that is that it isn't just the string theorists who can make mistakes and be wrong, it's all of us. You shouldn't believe any statement that a physicist makes, and including even me, including even the lies that I will tell you today. You shouldn't make it until after you've seen the data. And you just shouldn't take that seriously. So let me go on. Well, these two parameters that I was talking about, the Hubble parameter and, well, first the scale factor, the Hubble parameter, and the first slow roll parameter, it would be just about impossible on one graph to show this guy because it expands humongously by factors of e to the 60, e to the 120 over the course of parts of the universe that we're pretty sure occur. Even this guy you cannot show on any scale other than logarithmic because it increases by factors of e to the, or decreases by factors of e to the 56, or 10 to the 56. However, this guy, the first slow roll parameter, does not bounce around very much. You can actually plot it on a real scale, not logarithmic, all in one scale. And I will do that for you based on what we think the universe looks like. So it's best to go back. This is now, so the time scale is logarithmic. It's in terms of writing the scale factor as a constant times e to the n. And if you call this now, what it looks like is that. So you can see that actually epsilon has got less than 1. Getting less than 1 is the key threshold between acceleration and not acceleration. You can see that about 6 billion years ago it got less than 1. However, before that, it was about at the matter-dominated value of 1/2, or 3/2 rather. And there were significant events that we actually have data for at the time of recombination, which is when the cosmic ray microwave background came to us from, the time of matter-radiation equality, which is when the radiation, the relativistic matter, and the non-relativistic matter made equal contributions to the energy density, the time of Big Bang nucleosynthesis, when the lightest isotopes were formed. And if you just take the equations in something called the lambda CDM model and evolve it back, it gets better and better, closer and closer to epsilon is exactly equal to 2, back as far as we can go. We believe, again, from the cosmic microwave anisotropies, that there was this period of what's called primordial inflation. So this is the second time of the universe with epsilon less than 1. We believe that there was a phase when epsilon was very much less than 1, was almost 0, and that at the end of inflation, it, through a mechanism that isn't well understood called reheating, it hooked up to there. Okay, so those are significant events, and you should bear in mind that this is e-foldings and a highly compressed ordinary time scale. So in terms of years, this would be about 3,800 years after the Big Bang. This would be about 1 second to 100 seconds. This would be about 10 to the minus 32 seconds. But again, caveat, don't accept things unless you see the data. We actually do have data on this part up to here, no real data in here, and some data here.
How do we have data on epsilon from those things?
How do we have data on epsilon? So the power spectra that we can measure depend upon epsilon. So we have some data, we have some constraint on epsilon. The scalar power spectra goes like 1 over epsilon. And the tensor power spectra, so that we have two power spectra that we can in principle see. And this guy goes like G h squared over epsilon. This guy, which we haven't resolved, goes like that.
Yeah,
So-
what power spectrum for BBN?
Pardon?
What power spectrum?
Oh, not power spectrum for BBN. BBN, what we do is take theory and make predictions based on how it is that we run the thing through the time of nucleosynthesis and how long nucleosynthesis lasts. And that will, depending on what the Hubble parameter is changing, then almost perfectly like radiation
And
domination.
what elements in BBN?
Oh, let's see. So there's big debates in this field about whether or not you should use deuterium or lithium as the best measure of
About
it.
one.
Pardon?
About one of about two elements. Right?
So there are other elements. So helium-4 and then of course hydrogen. So the thing that you look at is ratios of this to hydrogen. So helium-4,
I thought
helium.
BBN and equilibrium and recombination were all in good shape before epsilon came along. So how did epsilon add to that?
Well, so they're just consistent with epsilon. So they're just consistent with epsilon equals 2. So you're right, they were in reasonable good shape. There actually is debate about BBN. There is, lithium is not agreeing exactly with the result that we would get from deuterium. But they are in pretty good shape, and they all are consistent with this picture. So they depend upon what the Hubble parameter was, not just its value, but also its time dependence. And its time dependence gives you what epsilon is, because epsilon is minus h dot over h squared. And they are completely consistent with epsilon equals plus 2. Is that okay? Okay. So first off, the part that's most conjectural about this is that part right in there. And again, I told you not to believe anything that we say unless we have evidence. What's the evidence that we have for this? Well, there actually are quite a number of reasons for believing in this phase of primordial inflation. I will give you what's, I think, the strongest one, which is called the horizon problem. The horizon problem is basically how it is that the universe got to be as homogeneous and isotropic as it was way back in the early universe. And it has to do with the fact that we can see early phases of the universe, and it looks like it was in thermal equilibrium to a huge part, although not in exact thermal equilibrium. For example, if we are sitting right here, we're looking back in time to the surface of recombination, the time when when the electrons and protons combined to form neutral hydrogen, and light began free streaming from us, we can see on the order of 3,000 regions which if you did not have a phase of accelerated expansion, if you just had epsilon equals 2 all the way back, would correspond to about 3,000 or 5,000, here I quote, regions that are so far apart that you cannot even have had them exchange a light ray in the amount of time that the universe has had in existence. Okay? And we can actually be quantitative about that by taking the homogeneous and isotropic geometry and then using it to say light propagates along null cones. It's light-like, so it has ds squared equals 0. Hence that tells you what dr is as a function of t. And that means that you can calculate the radius of the past light cone here, dt over a of t. That's this coordinate radius. You can also calculate the future light cone. That's this coordinate radius, the amount of time, the amount of distance that light can have propagated from the beginning of time. And the horizon problem is when you take the ratio of this guy to that guy, it winds up being a number very much bigger than 1 if you didn't have a phase of accelerated expansion in the distant past. There's an easy reason for understanding that. It's just that in order to have accelerated expansion, or in order to have decelerated expansion, you have a of t basically growing like t to power less than 1. For example, matter domination would be t to the 2/3. Radiation domination would be t to the 1/2, never greater than 1. So if you do that, this is t to a power less than 1. That means you can do the integral, And it will be growing. The result of doing the integral will be a positive power, right? If it was t to the 1/2, it would be t to the plus half. If it was t to the 2/3, it would be t to the plus 1/3 here. And that means that it's the upper limit that dominates, not the lower limit. In fact, you can take the lower limit to as negative as you want, as small a value as you want, all the way down to a equals 0, and you will not get it to grow past a certain point. This guy also, the upper limit dominates. And this guy's upper limit is later than that guy's upper limit, so you can see the problem, right? Inflation avoids that. This phase of early accelerated expansion avoids that because the accelerated expansion has a of t growing faster than t to the 1. So like t squared, or t to the 50, or t to the 100, or e to the t. If it grows like t to the 100, then when you do the integral, it's only 1 over t to the 99, right? And that means if you try and take this back to 0, you can get it to blow up. You can get it to be as big as you want. So inflation causes the lower limit to dominate, and that allows you to avoid this crazy situation where the radius of the future light cone at these early events is much, much smaller than the radius of the past light cone looking back. Okay, is that clear to everybody? And I think that is just an overwhelmingly powerful reason for believing that there has to be a phase of early acceleration. To say it more graphically, when we look at the cosmic ray microwave background, we see stuff that's almost in perfect equilibrium. It's the best black body in all of physics. And it's in thermal equilibrium to 1 part in 100,000. You probably are thinking that the air in this room is in thermal equilibrium, and it is approximately so, but it's not that good, not anywhere near that good. There are much, much larger fluctuations there. It is brilliantly good, but not perfect. We can see fluctuations in it. And we have to explain why it is that that's occurring, and inflation, you can see, will neatly do that. It says that all the parts that we see, if you had an inflating universe, just by taking this back far enough, an inflating universe would say that instead of looking like this picture, everything that we can see came from one region and could easily be in thermal equilibrium. So there are other reasons for believing in it, but that I think is a very, very powerful reason for it. The major part of my talk is to try and convince you that quantum gravitational effects from inflation are observable and are being observed right now. That might seem like a crazy, crazy statement, so let me just point out that there are 3 reasons why that's true. The first is that the Hubble parameter, the characteristic measure of quantum gravitational effects, is much, much larger during primordial inflation than it is now. So it's still so that this number is small, but it's not hopelessly small, not unobservably small. Compare that with what it would be if you plugged in this value that the Hubble Space Telescope guys got us. This would be 10 to the minus 122. We can't measure that. We never will probably be able to do that. Second reason is that there's lots of gravitational radiation and scalar radiation, spin 0 particle radiation that gets produced by an inflating universe. So if you have a universe that's undergoing accelerated expansion, it will produce radiation. Again, not really hard to understand, although I will be a little bit more analytic about that. It's just that you know that you get radiation from light when you shake charged particles, right? Well, when gravity is expanding these things, it does not seem terrifically unreasonable that if you're shaking those things, you should get radiation from it. I will be a little bit more analytic about that, but that's basically the idea. And the third very important thing is that there's a mechanism by which those perturbations that get produced in the very, very early universe can fossilize so that they will survive to very, very late times and can be seen now and are being seen now. So I've actually already sort of argued to you about why it is that this number is so much bigger than that number. It's just you take the lambda CDM model and evolve it back. H gets much, much bigger in the past. Let me go on to number 2, which is, forward, not backwards, which is why it is, this funny business about why it is that particles are produced in an expanding universe. And this is actually the hardest part of my slides to understand. So if you're having a little bit of trouble understanding this and you want to just take a nap, this is the time to do it. it comes from the energy-time uncertainty principle. So you know that there's not only a position momentum uncertainty principle, but also an energy-time uncertainty principle that goes that delta E times delta T is greater than about h bar. And the way that that's usually interpreted is saying that if you want to resolve an energy difference, delta E, you need to wait a time, delta T, longer than the amount given by that relation. In particle physics, it usually gets turned backwards and used the other way around as saying that virtual particles can exist for a very brief period of time. The idea is that if time is going this way, and you had an empty universe over here, and then you had a pair of virtual particles to emerge, one going this way and one going that way, they could conserve momenta. They could come off back to back so that this one's 3 momenta canceled that one's 3 momenta, but they can't conserve energy, right? The energy before was 0, the energy after is whatever the Einstein relation gives the energy to be. Okay, so they're not conserving energy. Nonetheless, we never resolve a violation of energy conservation. How can that be? Well, it can only be if that virtual pair lives for an amount of time less than would be given by the energy-time uncertainty principle. And you can understand a lot of stuff that way. For example, I think everybody's read the Feynman lecture type arguments about why this says that massless particles have 1 over r forces. You can also understand why massive particles have short-range forces. And I think since we're all physicists, I don't need to go into a lot of detail about that, so I won't. How does that change? That was all in flat space, where you didn't have A of t, where A of t was just 1. How does that change when you have an expanding universe? And the way that changes is that the wave number k is still a constant. So that comes from a nether symmetry, that comes from spatial translation invariance. That's still as true in an expanding universe as in the flat space universe. That's still a constant. But since lambda is not physical distance, it's just a coordinate distance, in order to make it physical, the thing that actually is physical is k over a. So when you look at the Einstein relation, it cannot be m squared c squared t to the 4th times c h bar k squared. It has to be k over a squared raised to the 1/2 power. Okay? And that has important implications. One thing is that you can't anymore write delta E times delta T. How many people have taught beginning physics? Let's see a show of hands. I've taught it more times than I wish I had. Okay, you remember when you teach beginning Newtonian mechanics, you always tell the humans again and again and again with boring, monotonous regularity, you tell them, look, work is the integral of force times distance, not the product, the integral. But it's like those pictures of, human talks to dog, Fido, to charge the perception of the physical means substituting representative functions, blah, 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 and what the dog actually hears, Fido, blah, 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 blah. Same thing with the humans. When you tell them it's the integral of force times distance, what they actually hear is that it's force times distance. And they want to always multiply a force times a distance. Then, of course, we know this. Physicists are evil. So we know this, and then we ask them a homework problem where they deal with a position-dependent force. And some of them come to us in tears almost, saying, wait a minute, the force is changing as a function of distance. Which force do I use? Which position do I use? That human is right on the verge of discovering the concept of integration. What it really is, same problem here. The energy is changing as a function of time due to the cosmological redshift, and the energy-time uncertainty principle becomes an integral. You created the virtual particle pair at t, you took it out at t plus delta t, and the condition for just barely obeying the inability to resolve a violation of energy conservation is this equation. And now, let's look at what that would be. Another thing is that quantum effects are always biggest from virtual particles, are always biggest for the particles that last longest, the virtual particles that last longest, right? Duh. If you want an effect due to them, you want them to last longest. That's always going to be when you make the mass 0, because that one comes in just positively squared. So biggest ones in curved space, as in flat space, are massless particles. Suppose you do that, then I can take away the square root, and it becomes just some constants times dt over a. Now I always try and tell the students that, that mathematical expressions have feelings. And you shouldn't really care what the humans think, because they're not going to be around much longer anyway, but the mathematical expressions have feelings, and we have seen that integral, dt over t. And in particular, there's a key difference between normal expansion, decelerating expansion, which is when the upper limit dominates, and if you take the upper limit to infinity, it grows without bound, and decelerating expansion, which is when the lower limit dominates, and you can take the upper limit to infinity, and you will not get a divergence. And we have seen that exact same integral. And what that is telling us is that I can take delta t to infinity, and if the thing started out long enough wavelength, no problem, I will never violate the bound. Hence, virtual particles that are a long enough wavelength can live forever in an inflating universe. Well, you might at this stage think, oh, great, so all we need is a massless particle, and then we can have them...
This has nothing to do with Planck's constant, right?
Yes, sure, the Planck's constant cancels on both sides.
Yes.
Right.
Always does. So this is a...
Oh, sure.
This is motivation for
Getting
let's
big
say-
quantum
let's say
effects.
propagating a wave, sort of adiabatically propagating an early perturbation and saying it lasts a long time when everything stretches it out.
Well,
So
actually, I'm going to motivate this for creating perturbations, for causing them to appear just out of the vacuum and not ever have to disappear.
Well, we don't necessarily have to talk about the mumbo-jumbo type of virtual that's usually bandied about. So if there's some random perturbation, do I follow that this argument is that if it's a long enough perturbation, when everything stretches, it's still around? Is that what this is saying?
No, I don't think so. So this is saying that it occurs out of nothing, that nothing caused it. It wasn't sourced by anything, and it doesn't have to disappear due to energy conservation. It can survive forever. So it can just be ripped out of the vacuum without there. Now, it is true.
Regardless of the cause.
Oh, okay,
The
so...
cause is not under discussion.
Uh-huh.
The point of this, the reason you brought it up,
Yes,
is, am I right, I'm trying to follow,
yes.
is that
Good.
once you have a given wave, if it's a long enough wave, that the nature of an accelerating scale factor is it'll pull it out and we can still see it today.
No, that's not my
Then
point.
what is the sense of it?
So my point is that there never are energy fluctuations. So usually there would be a factor going like e to the I omega t, e to the minus I omega t, that would cause the thing to fluctuate rapidly, so that if you had it live too long, there wouldn't be any net effect of it. That's not happening here.
All right, 'cause
Fluctuations
the
are just
factor is
killing.
dominating time.
That's right, because the redshift, the energy of the thing is, the energy of the fluctuation is just redshifting so rapidly that it is not preventing you from having it exist forever. Okay, so at this stage, so to restate the conclusion again, any massless particle which is long enough wavelength initially can just exist forever. A virtual particle could just exist forever. At this stage, you might believe that all of the massless particles are contributing huge quantum fluctuations, but you'd be wrong about that, because there is a killer symmetry that causes almost all massless particles not to contribute to perturbations. For example, there is no massless fermion perturbation. There is no vector, there is no photon, there is no gluon perturbation. None of those things contribute. There is no conformal scalar perturbation. The reason why is because of a killer symmetry called conformal invariants. And to make that clear here, I first want to do a change of variables from t time to what's called conformal time. So it's just a one-dimensional change of variables. d eta is dt over a. And if I just take the dt squared term and rewrite it, then it becomes proportional to a. So the whole invariant element is now just proportional to a squared. And in terms of a relativity geek, he would say that that means the metric is just a squared times the metric of flat space, the one that you're used to. Okay, so that's just a change of coordinates of this particular geometry. Conformal invariance has to do with invariance under a particular transformation. So it's just like gauge symmetries, like where you take a photon field and do a mu goes to a mu minus d mu of theta, where theta is a function of space and time, it's characterized by a parameter called omega. And what the transformation is the metric goes to omega squared times g mu nu. Vector potentials don't change at all. Fermion fields go to 1 over omega to the 3/2, and scalars go to 1 over omega. And an example of a conformally invariant Lagrangian would be electromagnetism, where F mu nu really is d mu a mu, just like it is in flat space. So here you have a G inverse and a G inverse. Since they're G inverses, they get a 1 over omega squared. You have two of them. You have a 1 over omega to the 4th. Assuming that we're still living in 3 plus 1 dimensions, this gives an omega to the 4th, and you can see that those guys cancel, so electromagnetism is conformally invariant. A theory which is conformally invariant has the property that its L, just as I showed you here, is exactly the same in conformal coordinates in this expanding universe as it is in flat space. What does that mean? Well, what it means is, see, I left an important part of this argument out. I said, assume that a perturbation is ripped out of the vacuum, that a perturbation of virtual fluctuation exists, and then the rest of it was kosher analysis. But I didn't tell you how probable it was for that to occur. In flat space, that probability is just a constant. You can see for any conformally invariant theory that then dn d eta, the probability per unit conformal time, must be that same exact constant. What does that mean in terms of physical time? It means just using this, that dn dt is that constant over a of t. Hence the probability falls off like 1 over a. So what that means in words is that any massless particle, which is conformally invariant, that happens to be admitted, can live forever, but very, very few are going to be admitted. That's why there's no photon power spectrum. There are two violations of that. Massless minimally coupled scalars, those are just the simplest kinds of scalars, and gravitons. They both are massless, but not conformally invariant. And this actually is the hardest slide. After this, it will all get easier. To do it, I want to just remind you of the one-dimensional harmonic oscillator, whose Lagrangian is that. The dynamical variable is q of t. It could be written as a raising operator times a mode function, u of t, which is just an exponential. And I will write it in this seemingly stupid way, as instead of e to the minus I omega t, I'll just write it as e to the minus integral dt prime of omega, but of course that's omega t, right? Because I can do the integral of a constant. And if I plug in the energy, if I look at the expectation value of the energy operator, m over 2 q dot squared plus omega squared q squared, then it will be u dot squared plus u squared. When I plug these things in, do all the algebra and everything, I get the famous result of half h bar omega, right? Okay, do the same thing for a massless minimally coupled scalar in this general background, this general homogeneous and isotropic background. It's just the simplest kind of scalar. If you write out all the metrics and everything, it becomes an overall factor of a to the 3rd from the square root of minus g times a phi dot squared minus the spatial derivative terms. That's all it is. It doesn't have any other terms, no mass terms, no higher interactions. And what that tells you, if you Fourier transform it, where the del is going to become a k, is that each k mode, each k vector mode, is itself a simple harmonic oscillator, but it's a simple harmonic oscillator with a time-dependent mass that's growing like a to the 3rd of t, and a time-dependent frequency that's growing like k, or falling off like k over a of t, okay? I know that was a little bit complicated, maybe did exceed a little bit the first-year graduate student bar, but not too much, and that's actually all I need. You cannot solve the mode equation for this thing for a general a of t, although you could solve it for the epsilon equals 0 case, and the exact solution is this. Almost all of it you can understand. For example, this factor is just that. This factor is just that. The one part that you can't understand is that. That's coming from the time dependence of m and a of t. And you also can understand that the energy operator is just that. At any instant, it's a harmonic oscillator. It's just a harmonic oscillator with a time-dependent mass and frequency. And if you evaluate that and plug that in here, what you get is two terms. One, the term that is the good old 1/2 h bar omega t. The other one is something which is interpreted as an occupation number. You see, at any instant, this is a harmonic oscillator. So at any instant, its energy must be h bar omega times a half plus n. Here's what n is, the occupation number. And if you read that off, that's h times a of t, and a of t is growing like a bat out of hell. It's growing exponentially, divided by 2ck. Okay? And you might compare that with the result for a conformally invariant theory. So all of those factors that might have irritated you a little bit that I was dealing in the qualitative stuff have analogs over here. For example, the energy time uncertainty principle argument was just saying that this guy cuts off as time goes on and you don't have oscillations of that. The argument about conformal invariance cutting off the probability of emission is just that factor of 1 over a that appears there. Okay, and if you did this for a conformally invariant theory, you wouldn't have that term, and the occupation, the only thing you would get in the energy is that. It would just be 1/2 h bar omega, and the omega would be falling off with time, and you'd wind up getting an almost zero effect. Further, another very important thing, so by the way, at this stage, I'm done with the demonstration that particles are created copiously during inflation, and you can see even when they happen. This occupation number gets to be of order 1 when HA is approximately equal to CK, right? That's called first horizon crossing. And after that, it grows exponentially. And guess what? Unless the string theorists have changed something, so I was meeting with people all day today, and I didn't have time to check the OGPTH website, but unless they have changed something, there are a lot of K vectors. Is that still true? Are there still a lot of K vectors? Good. So every one of those K vectors is showing that behavior. That is the source of these effects. That's what's causing this. It wouldn't do any good, though, to have that happening in the early universe if these things didn't fossilize in and wind up being there so that we could see them even at late times. And you can see that happening, too. That's happening because this integral is approaching a constant as time goes to infinity. Because remember, A is growing very rapidly so that the integral converges. This A is just canceling that. This one's dying off, so this guy just approaches a constant. So there's the final thing that you needed to see, that these modes fossilize, okay? And they can survive during late times. Okay, well, we actually see them. We have data. Here's a full sky map of the Planck survey of looking at temperature anisotropies in the early universe. It's color-coded so that red is hot and blue is cool. And these are very, very small fluctuations. It's almost perfectly black body at 2.7265, whatever it is, degrees Kelvin. We actually, like I say, have data for this guy, and it is a constant times k over k naught to the n sub s minus 1. We know this number, again, it just blows me away. We know it to 3 significant figures. We even know that index to several significant figures. We have not yet measured the tensor power spectrum. That you probably heard last year. There was a measurement by the BICEP collaboration at the South Pole, which was claiming to have detected that. It later turned out that what they were seeing was really just dust. Although that the limit that they obtained on that was important because that helped us put a better limit on what the tensor to scalar ratio is. There are many, many, many new polarization probes motivated by this thing, which are coming online soon, and I hope very, very much, again, although you shouldn't believe anything until you see the data, that we will see a tensor power spectrum within the next year. And the prediction, the theoretical prediction for these two results in terms of G and H bar and everything look like that. Okay. I am cruising on empty as far as time goes, so I think I'm going to just make these points and then jump to my conclusion here. Okay, so what I want to hit you with is the idea that this is the first quantum gravitational data that's ever been seen. By the way, why is that? It's because of these theoretical predictions. First, the theoretical process that I told you about was occurring in quantum gravity plus matter. Second, the prediction has got h bar g. Whenever you get the h bar number and the g number together, that's quantum gravity. And there are a lot of, I think, kind of foolish statements that are going around in the literature about that, where people are denying that, and they're denying that on the basis of imposing much, much higher restrictions on what they count as quantum gravitational data than they count on ordinary normal gravitational data, and I would like to just explain to you why it is that I think they're wrong. Okay, so there are three arguments that are made against this interpretation that this is quantum gravitational data, the first ever collected. The first is that it's not quantum gravity if it's only tree order. These are tree order effects. They are not quantum loop effects, they are tree order effects. They're the first term in that series in quantum gravity. Okay? And there are a lot of, I think, foolish people who are saying, oh, well, then it's not quantum gravity. Well, it's maybe not the most interesting thing in quantum gravity, but it is quantum gravity, and there are a lot of perfectly good quantum effects which are tree order effects. The photoelectric effect, for example. Beta decay, Pabba scattering at lowest order. All of those things are tree order effects. It is just unreasonable to rule this out as a quantum effect just because it's tree order. Second argument that's sometimes made is that we've seen the scalar power spectrum, but we haven't seen the tensor power spectrum because BICEP turned out not to be right, and we haven't yet resolved the tensor power spectrum. And these people, these I think kind of foolish people, will say we need to see gravitons before it's really quantum gravity. That's wrong. That's actually exactly backwards. And further, if we adopted that same constraint with the solar system, we would not count that as a measure of classical gravity. The best measurements on general relativity are all coming from the gravitational response to classical matter. We only have one measurement about gravitational radiation in classical general relativity. That's the spin down rate of the binary pulsar system. If you adopted that same constraint of ruling out, of insisting that it only be gravitational radiation before you would count it, you would throw away almost all the successes. You'd throw away the precession of perihelion of Mercury, laser radar ranging, all of those things would go away. So that's, I think, just silly to do that. And further, it's especially silly from the point of view of quantum gravity because the scalar response is actually the most interesting one. It's the gravitational response to quantum matter. And you remember I told you in the problem of quantum gravity, the two things that are wrong are first that the number is too small to get a thing. Well, here it's not too small. We're actually getting a result. But the second problem is that theory is predicting that the loop effects are divergent. That divergence, the lowest order divergence, the one at one loop order, is not coming from gravitons. Gravitons do not cause a problem at one loop order. They can and do cause a problem at higher orders, at two loop order, but the lowest order problem is due to quantum matter. So if you took a quantum gravity expert such as myself, and he was not kind of foolish, and you asked him, look, you can only see one of them, which do you want to see? This is the one I'd want to see. I'd want to see the scalar one rather than the tensor one. It's more interesting. It tells me more about what's going on with quantum gravity than the other one. The final argument is that it's not quantum gravity unless you can predict it uniquely, because these predictions all depend upon what the Hubble parameter is, and we don't know exactly what the Hubble parameter is. We don't have a unique model for what is causing inflation the way we have a model for what's causing the gravity in the solar system. But that's, again, just silly. I mean, we can, Casey works on dark matter, for example. One of the prime pieces of evidence about dark matter is rotation curves of galaxies and virial flows inside galactic cluster. All of those are undoubted gravitational effects caused by something that we don't know yet. We don't reject those things as gravitational effects just because we don't know the thing that's sourcing them. Why should we reject this thing as a gravitational effect just because we don't know what's sourcing them? So I really think that that's silly, and I think you should accept that. This has an effect on quantum gravity, but I'm actually now over time, and the people who taught me never to do that, so I will just skip ahead to my conclusions, and I will stop torturing you and end with my conclusions at this point. So conclusions are that I think that we're on the onset of a golden age in quantum gravity. We're seeing the theory mature from being one of just crazy speculation where you could say anything you want to a point where there's hard data and it's actually changing the way it is that we view physics. That's coming from a concatenation of three things. First, the inflationary Hubble parameter is much, much bigger than now, and that means that quantum gravitational effects during inflation are small, but not hopelessly small. Second, the universe was accelerating, and that means that gravitons and massless minimally coupled scalars are getting produced copiously, exponentially big numbers, and there's large numbers of Ks. And third, that there's a mechanism for which through which perturbations can fossilize and get stuck in the universe to survive for much, much later times so that we can see them. The primary effects are the production of inflationary gravitons and massless minimally coupled scalars. This thing is the gravitational response to quantum matter. That has been resolved to 3 significant figures. It blows me away that that's true. This one, the tensor power spectrum, has not yet been resolved, but I hope. God, if you're listening, I know I've been evil. I know I did a lot of bad things to the first-year students, but come on, I'm a physicist, you know that. You made me this way. Anyway, so if he's listening, he'll let us see that soon. There are a lot of secondary effects that I didn't get to tell you about, which is actually what I work on, which is loop corrections and what this stuff does to other quantum fields. Those effects, we have enough data potentially available in 21 centimeter radiation from forming protostructures early in the universe to potentially be able to resolve that. It won't be easy or quick, but over the course of the lifetime of the students who are around here, we might eventually see that. There is enough data to do that. And crucial questions that this is posing for fundamental theory, some of which didn't even exist as little as 2 decades ago, are what is causing the late time phase of acceleration, this thing that embarrassed us all so much, what drove primordial inflation, and how is it that we define observables that allow us to correctly quantify these things the same way that Casey and John can using particle theory, using the particle theory S matrix and rates and cross sections. We need analogous variables for cosmology that will allow us to quantify those effects in as unambiguous a way so that we can talk about that. And those are all open questions, and that's good to have a lot of open questions, and it's an exciting time, and I hope I've communicated to you my excitement about it. Thanks very much. I'm sorry for having gone over questions.
This is kind of a weird question because it's tangentially related, but since you made the point about MMCs and gravitons having a way to live longer than initially expected, are there observations that cosmic ray physicists can make with regard to high energy particles interacting with them if the cosmic rays are traveling over wide cosmological distances?
Well, in a certain sense, yes. That is what the CMB perturbations are. So we see photons interacting with them. So the thing that we see with the cosmic ray microwave background is photons interacting with the scalar fluctuations in gravity. We haven't yet seen the effect due to the polarization that photons would pick up due to that. But yes, that is definitely an effect. And you can think about other particles too. And that might be especially relevant to some of these secondary effects that I didn't have time to tell you about. So, which is my fault, not yours, by the way. But there are a lot of secondary effects. So if you create all these gravitons and scalars, then they will do 2 things. They will interact with themselves, and they will also change the kinematics of other particles that try and propagate through those things. And that can and will create effects on those other things, and trying to tease out measurable signals that would survive to the current day of those effects is, I think, a very, very interesting and important set of studies, and one that I'm certainly working on very, very hard. So it's an excellent question.
Are those effects at all related to violations of Lorentz symmetry, or are those only like a small overlapping section of this?
Well, I don't think they're violations of Lorentz symmetry. What they might be is violations of approximate thermodynamics, or violations of approximate thermal equilibrium. For example, the production, gravitons will create a bath of gravitons that photons try and propagate through, and that will create a sort of a minimal amount of excitation of photons, which would not be there without the production of inflationary gravitons. Without that, they should just, the vacuum energy should just be redshifting like a half h bar omega. This is going to change that. And what that should do is to create long wavelength photons in excess of thermal equilibrium. So it should be that our universe is getting a constant injection of these long wavelength photons that are far in excess of what thermal equilibrium would have produced at that wavelength. Could we see that? Well, right now I don't yet see a way of seeing that, but that would be the kind of effect that you might see. This, the same thing that my wife wrote her thesis on, was the same kind of effect occurs in fermions. Basically, she studied massless fermions, but at those scales, everything is a massless particle. And what she showed is that they experience a progressive excitation of their amplitudes. Again, they are exactly conformally invariant without these effects, and they would just redshift away. So you would not see any production of fermions. With these effects, they get produced. You might imagine eventually that that is a mechanism for causing baryogenesis in a more advanced theory, a more complicated theory, to occur during inflation rather than after inflation. So there are definitely mechanisms that you could think of that would produce observable signals. So far, no compelling ones have been written down and analyzed yet, but they're definitely, the analysis is not done, and there definitely are things that you could look at. Yes?
Okay, I can see why people complain that this calculation, this style of calculation in the background field, with the quantized scalar in the background field, they don't like it as quantum gravity. But I can also see why you can defend it, because you can say that there's all kinds of effects like this that are valid quantum mechanical effects in quantum mechanics. Let me ask you, because I just thought of this while you were explaining it. When we talk about quantum field theory for gravity, for the metric, we're changing the configuration space. We're proposing a Hilbert space for quantum fields rather than the classical. And the first prototype of that is black body radiation, where there's a Rayleigh-Jeans problem with the photons, because the photons had a certain classical configuration space, phase space. And in the quantum field theory, which is a black body problem, the counting of states is different, and it's okay. So can't I take that as proven that quantized gravity exists because there's no black body problem? I haven't seen the Rayleigh-Jeans problem for gravitons either in the early universe or
That's an
in
interesting
ordinary
argument.
boxes.
No, that's an interesting argument. Yeah, that's, you might publish that. I would say that that's, if you publish that, look, I know the elite physicists will just say that that's ridiculous, but if you list me as a referee, I guarantee you I'll accept it. I would say it's an interesting and completely...
More questions!
That's a completely okay argument. Classical effects would produce a classical ensemble of radiation from the early universe, no question about it, and we ought to see exactly the same problem occurring from there as would occur in the classical electromagnetic problem, the same thing that led Planck to propose quantization of ultimately of everything. And yeah, I think that's I hadn't thought of it, but I think that's a completely correct argument.
What kind of data will convince you that actually you're going the wrong direction? Let's say that they discover that R, the ratio of tensor to scalar, is, let's say, not less than 0.1, but less than 0.01. Will that kind of tell you that maybe you're doing something wrong?
No matter how small R is, I wouldn't be convinced that I was wrong, because right now you can have models that will get R arbitrarily small. I think you have to separate about what you would mean by what you think is wrong. So I don't think that there is anything that could convince me that there wasn't an early accelerated phase of expansion. I think the data on that is just overwhelmingly powerful. There is nothing that could convince me that that has not occurred. Well, let me rephrase that. If the Lord appeared here in fiery letters and said,
Let's
Richard,
not talk
look,
about the Lord.
I know, I made the universe, it didn't happen that way. If you'd like to see a picture of it, I'll show you, but trust me, it wasn't that way. I'd be convinced, I could be convinced, but
You trust him just because he said so?
fiery letters and everything, it would not take very many miracles to convince me that there was a God and he was telling me how the universe was created. But I would say the evidence on an early phase of accelerated expansion is just overwhelming. What caused it is, I think, completely up in the air, and I don't, unlike many people in the community, I don't have any prejudices for what caused it. So if you ask Andre Linde, it's got to be scalar-driven inflation, got to be the multiverse, eternal inflation, blah, 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 blah. I don't have any prejudices about that. So in my own belief system, I could accommodate the data whichever way it went. Big R, small r, whatever it was, I could accommodate that. And it wouldn't bother me. One thing that would give me pause, however, would be if it turned out that the scale of inflation was very, very small. For example, electroweak scale. It has been proposed that it could be as low as electroweak scale. I think that would be very, very hard to accommodate within things that I understand.
That would lead to small r.
That would lead to infinitesimal small r, yes.
Exactly.
But that would, I would say, bother me a lot.
So we asked a similar question to the Florida people, Suji people, right? When do you stop studying supersymmetry? Is it 10 TeV, 100 TeV, or are you going to keep going on? So this is always tied with the fine-tuning issue.
Well, so any models that have been suggested for inflation, seriously suggested, you know, when you go down to r equals 10 to the minus 6, none of those would bother me. Those are all okay as far as I'm concerned. I'd prefer if r was much bigger. I'd prefer if r was just below the current measurement. But one of the big problems that we have here is that we just don't have a good model of inflation. So, in fact, I listed that as one of the key problems is we don't have a good model of what drove primordial inflation. I have my own beliefs. I believe that what drove it is not a scalar field, but actually just the quantum gravitational back reaction on the gravitons themselves. That as you get gravitons produced, they gravitate at some level, so they try and slow the expansion rate down. You keep having this process go on and on and on and on. After more and more and more e-foldings, eventually you might believe that it's going to stop inflation. That's what I think happens. But I could be happy with the scalar-driven inflation if they have data for that. If they measure R and measure the tensor power spectrum and show that the single scalar consistency relation is obeyed, I would be happy accepting single scalar inflation. Wouldn't bother me.
Well, let's thank Professor Woodard.
Say, Richard, I will totally argue with you about gravity.
Monday, 8 a.m.
The question depends on what happens in the work. Why doesn't it start?
That's a good question too. So the way conditions and stuff like that, my own state now is migration large cosmological. I need bones to respond.
Yeah.
So here's what
How did it start?
well, I would say that what's crossing into to Woodard is that we don't
Now,
measure
there's
all
all
of
these
the
different,
expansion or the expansion rates, and it works really well on gravitational effects.
Yeah, that's
So
right.
if it is very positive, I think what we're seeing is a slow expansion rate that's the result of a huge amount of gravitational radiation that is causing the universe to be held together by its own self-gravitation right on the verge of gravitational collapse.
Polarization of
Because it was very, very close to gravitational collapse, and that was the result of a careful balance between the amount of gravitational
That's not established.
work it's produced.
Polarization is measured.
And the universe fairly recently went a phase transition from being radiation to being out of
Just stop.